Erisa Hasani. She will speak on the compactness threshold in the critical Kirchhoff equation. Please.
Hello, thank you for having me in this webinar. So I'm going to share my screen as well. Okay. I hope you can see this.
Yes. Yes.
Okay, thank you. This is work I did with Dr. Pereira for my master thesis. And okay, so let me begin. So for a bounded domain in Rn and n bigger or equal than 3, we have this Kirchhoff equation for the critical case that was mentioned before as well, where A, it's non-negative, B is positive, and some lambda parameter positive. So solutions of such problems were obtained in dimension 3 and 4, and here are some references from people that did work in there. But instead, for our studies, we considered also a power to this non-local term for a positive power, where gamma will be between 1 and plus infinity. And A and B again are as before, and lambda is positive. Weak solutions of this problem will coincide with critical points of this given functional in the Sobolev space. But also, instead of considering this problem that we had with this power, instead we can think of it as a function of this argument for this side and some properties that it has to satisfy. And for this lambda u, we can have a more general function for it. In particular, we have a problem of this type. And again, omega is bounded and in that dimension. So this f function will be a Carothers function satisfying this subcritical growth of this power p between 1 and 2 star, and for some positive a1 and a2. Once again, weak solutions of this problem will satisfy this equation here, which is just integration by parts if anything, and we also have the corresponding functional C1 functional in the same space, and this h here will denotes the primitive of this h, and big F denotes the primitive of this function f that we mentioned before. Here's some notations that will be useful. Again, this capital H was the primitive of small h, and also this we defined by k of t, this difference here for any t bigger or equal than 0. And as in Dr. Pereira's presentation, we denote by S, again, the best Sobolev constant of the Sobolev embedding. In addition, we defined this set I for t positive such that this function h of t is bounded from above by this number here, s to that power and t to that power. Okay, and also let us denote by lambda 1 gamma the first eigenvalue of this nonlinear problem, eigenvalue problem, and note that if we take gamma equals 1, this term goes away, and also this term goes away, so we're left with the first Dirichlet eigenvalue for the Laplacian in omega. Okay, so now, as I said before, since we're generalizing the problem, we have some assumptions on H. And in particular, that would be for these constants A1 to AN positive, these gamma i's between 1 and 2 star over 2, and this mu i's bounded by these lambda i's. And we want this k of t, and remember this k of t was this, I went too far, this difference in here. So we want that k of t function to be bounded from below by the sum, and also we want this difference in big F and small ft bounded above from this term over here, and that to hold for almost all x in omega and all t in R. We also require that this k it's also subadditive, meaning for any T1, T2 positive or 0, this inequality holds in this order. Finally, we have the last assumption on H, where we want this fraction here to be strictly decreasing for any T positive, and for this relation here to hold. Okay, so here's an important proposition we used to prove the main result, which I will introduce in a second, which states that if we have a sequence in UJ sequence in H01, such that J prime of UJ will go to 0, UJ converges weakly to some U, and this difference in norm squared goes to some T, then we show that if either T will be 0 or T will be in that set I. And if I it's empty, then every bounded sequence in UJ satisfying UJ prime, J prime UJ going to 0 has a strongly convergent sequence. And now here's the main result. So in the case where I it's not empty, we have the following. So we define the C star as the infimum of K of T, and K of T was that difference from before, over the set I. And we show that then our functional J will satisfy the PSC condition for all such C less than C star. And in addition, if this equation here, H of T, so it was in the set I that was less or equal than this one. So if we have equality, then if this equation has a unique solution T naught, then we can explicitly find this C star given by K evaluated at T naught. And in particular, this C star will be positive. Okay. Okay, so for the case for problem 2, which was the model problem, if you remember, with that power, we have the following results. So if gamma is between 1 and 2 star over 2, and A and B are positive, and lambda is between 0 and A lambda 1, which was the first eigenvalue for the Dirichlet problem, and then let T naught be the unique solution, positive solution of this equation, which then if we set C star to be equal to this number, then we can show that J will satisfy the PSC condition for all C less than C star, which really follows from this main theorem. Okay, and then now for the case where gamma is equal to 2 star over 2, then if we have A positive, B between 0 and this number, and then lambda between 0 and A lambda 1, then we can find C star to be given by this number, and then again the J functional will satisfy the PSC condition for all C less than C star. And for the second part is that if A is bigger or equal than 0, B is bigger than this number, then J will satisfy the PSC condition for all C in R, and that will be in the case where I it's empty. The other case, the last one, is when gamma is bigger or equal than 2 star over 2. And then if this inequality is satisfied, then J will satisfy the PSC condition for all C in R. And again, this inequality here comes from trying to show that I it's empty. So these are the conditions that need to hold for the parameters for that to happen. Here's so for the classical case, if we in a result in what we have, if we take gamma to be equal to 2, which is the original Kirchhoff equation for the critical case, then we have the following results for C star. So if n it's equal to 3 and A and B are positive, lambda between 0 and A lambda 1, then C star can be found explicitly as this expression over here. And this was computed before in other papers. So for dimension 4, if A is positive and B is between 0 and this number, then and lambda is between 0 and A lambda 1, then we can compute C star to be equal to this number. Now for the cases n equals to 4 again, a positive or 0, but instead of b being less than that number, we have b being bigger than that number, then c star, well, this notation means that we will have the PSC condition will hold for all c. Okay, and then finally for the case where n is bigger or equal than 5, and this relation here holds, then again we will c star will be all positive numbers. Okay, and then okay, so now some existence results. So in the case where gamma is between 1 and 2 star over 2, the first one we saw, and b it's positive and n it's bigger or equal than 4, then problem 2, so the original problem that we studied, has a non-trivial solution for any lambda between 0 and a lambda 1. And for the case where gamma was equal to 2 star over 2, then if a it's positive, b is between this number, and n is bigger or equal than 4, then we have a non-trivial solution for lambda between 0 and a lambda 1. For the cases where a is equal to 0 and b is bigger than that number, then we get a non-trivial solution for all lambda positive. And in the case where a is positive and b is again bigger than that number, we get two non-trivial solutions for lambda bigger than a lambda 1. Okay, and for the case where gamma it's bigger than 2 star over 2, we will get two non-trivial solutions again for lambda bigger or equal than a lambda 1, given that our parameters will satisfy this inequality here. Okay, and for gamma equals 2 and n equals 4, if a is positive and b is between those two numbers, then we get a non-trivial solution for lambda between 0 and a lambda 1. And then if a is 0 and b is bigger than this number, then we get a non-trivial solution for lambda positive. And finally, if a is bigger than 0 and b is bigger than this number, then we get two non-trivial solutions. And the difference in a non-trivial solution and two, it's because different methods were used in the proofs. So, okay. And finally, for the case where gamma equals to 2, and so for the classical Kirchhoff equation for the critical case, if for dimensions n bigger or equal than 5, we get that if this inequality is satisfied, then we can get two non-trivial solutions for any lambda bigger or equal than a lambda 1. And I think that was the last corollary I included, and here are some references that I mentioned before. So, okay.
Okay.
Yes, that was quick.
Thank you for your nice talk.
Okay, thank you.
There are remarks, questions? I have a curiosity.
Yes.
The two solutions are some information of this solution are local minima or just critical points of the energy functional?
There were critical points of the functional. I don't think
critical points.
Yes.
Okay.
So. But just the methods for the ones that we got one non-trivial solution, we used the mountain pass theorem, and for the other one we used a different method. That's why.
Okay, thank you. Okay, there are some. Okay, thanks again.
Okay, thank you.